Hello, welcome back. This lesson involves the concept of the cube root, and also we'll be talking about higher order roots. In other words, you can have not only square roots, but you can have cube roots, you can have fourth roots, you can have fifth roots, sixth roots, seventh roots, and on. But to be honest with you, reality is square roots, which is what we've covered in the past, is by far the most common radical that you're going to run into in real applications. However, we do run into cube roots, we do run into fourth roots, so we need to understand the properties of them. Now, right off the bat, I want to tell you something here in the first minute so that if I lose you, I can at least impart this one thing to you before we get into the problems. I was harping on it over and over again when we did the square roots. I said when you take the square root of a negative number, it doesn't exist. Really, the right way to say it is you take the square root of a negative number, it's not a real number. There is no way that I can multiply two real numbers together and get -4. If they're the same number, like 2 times 2 is 4, -2 times -2 is also +4, so they never come out to be -4, right? Now it turns out that that property of square roots, where you can't take the square root of a negative number without getting into imaginary numbers, we're going to talk about imaginary numbers later, that property also extends to any root that you have that is an even number. So I told you can have square roots, which is a root with a number 2. It's involving kind of a square, the number 2. But you can also have fourth roots. You can have sixth roots. We're going to talk about what all these are. But see how they're even numbers? Second root, which is a square root, fourth, sixth, eighth, 10, and so on. All of those have the same property that you can't take those roots of a negative number for the same exact reason. If you try to figure out something to multiply by itself to give you a negative number, if it's a fourth root or a sixth root or something like that, it's not going to exist. You're never going to be able to find a real number that works. So the bottom line is when you have square roots, you can't take square roots of negative numbers. If you have fourth roots, you can't take fourth roots of negative numbers. If you ever deal with something crazy like a sixth root, you can't do it and do it with a negative number either. It's always going to be something imaginary, right? Now, on the flip side, in this lesson, we're going to learn about cubed roots, which is a number 3. Turns out you can actually take cube roots of negative numbers. And the properties are the same with odd number roots. So third roots, fifth roots, seventh roots, and so on. You can always take those types of roots of negative numbers, right? But you can't do it when you have an even root. So we're just going to introduce the concept of cube roots, but in the back of your mind, just keep in mind, you can't take the square root of negative numbers. And also that applies to any even root. You can't take fourth roots of even numbers, you can't take sixth roots of even numbers, and so on without getting an imaginary answer. But when it comes to cubed roots, you can take the cube root, of negative numbers. And the same thing applies to the odds. You can take the fifth root of a negative. You can take the seventh root of a negative number, and so on. I just want to put that out in front because it's really important you understand that. And so as we solve the problems, I want you to keep that in the back of your mind. What is a cube root? It's very easy to understand. The way you write it is you put the number underneath the radical as usual, but over here you put the number 3. This implies that it's a cube root. So what we were doing before had the square root radical, and we just don't write the invisible number 2 right here. When you have a radical by itself, you just automatically know that it's a square root. So where that 3 is there, it's just kind of an invisible 2 for regular square roots. But for third roots and fourth roots and so on, you have to write the number. Right? So what does it mean? We say that the third root or the cube root of 8 is equal to 2. By direct analogy with what we've learned for square roots, why do we know that that's equal to 2? Because 2 times 2 times 2, 2 times 2 is 4, 4 times 2 is 8, gives me back what is underneath here. So with square roots, we were trying to find a number that multiplies by itself, right? Just 2 times, right? By itself to give me the number. But cube roots, you're trying to figure out what number multiplies by itself 3 times to give me the number. And likewise with fourth roots, you're trying to find a number what multiplies by itself 4 times to give you the number. If you had a fifth root, you should be trying to figure out what is the number that multiplies by itself 1, 2, 3, 4, 5 times to give me the number back. The answer is 2 because 2 times 2 times 2 is 8. All right? What if you had the cube root of 27? You have to put that 3 here to tell me it's a cube root. The answer to that is 3. Why? Because 3 times 3 times 3, 3 times 3 is 9, 9 times 3 is 27, and I get back exactly what is underneath here. What is the cube root of 64? The answer to that is 4. Why? Because exactly the same thing. 4 times 4 times 4, 3 times. I'm doing it 3 times. 4 times 4 is 16. 16 times 4 is 64. So I recover back what's under the radical by multiplying it 3 times. All right? So just like with square roots, you had perfect squares. These are perfect cubes. So the answers that we all got were whole numbers, just like with the square root case. But of course, you can take cube roots of any number you want. You can take a cube root of 120, like this. Cube root of 120. How do I figure that out? Well, we're going to learn in a second how to use a factor tree. But really, just trying to think of a number, a whole number that multiplies by itself, there's no whole number. There is an answer to this, just like there's an answer to square root of 59, but it's not a whole number. There's no whole number that multiplies by itself 3 times to give me 120. And here is where I'm going to kind of introduce the concept that I talked about in the beginning. If I have negative 27, and I take the cube root of that, what do I get? We all know that if it's not a cube root, if I take a square root of negative 27, the answer is not a real number. There's no way that I can get negative 27 by multiplying something by itself, you know, just the 2 times, right? But this thing actually does have an answer. If it's a cube root of a negative number, the answer is actually negative 3. You actually can do that. Why? Because negative 3 times itself again. You see what's happening to the sign. Negative 3 times negative 3 is positive 9, but you still have times negative 3, which makes it negative 27. So the only reason we couldn't do it for square roots is because there's no way to multiply something by itself and get a negative number. But when you're multiplying something by itself 3 times, the sign can flip-flop and you can get a negative number. So cube roots of negative numbers are real. That's what I introduced in the beginning. Square roots of negative numbers are not real. Cube roots of negative numbers are real. And those properties extend to the even roots and the odd roots. So second root, fourth root, sixth root, and so on. You try to do that with a negative number, doesn't work. But cube roots, fifth roots, seventh roots, ninth roots, those are all odd roots. You can take those of negative numbers and get a real answer. So don't sit there and tell me this is imaginary or something else, because it's not. You actually have a real number. Okay? All right, let's move right along and let's take a trip down memory lane. We've learned how to do this just by thinking about what it means, but now we need to apply the concept of the factor tree to do the same kind of work that we did for square roots. If we had 125 and we wanted to take the cube root of it, what do? We do exactly what we did for square roots. We try to figure out what times what will give me 125. And so with the help of your calculator, you could probably figure out that 5 times 5 times 5 is 125. Why? Well, because 5 times 5 is 25, times 5 again is 125. Another way to write it is, if you didn't really think of that or know that, just remember this. 5 times, let's take this one off. 5 times 25 is equal to 125. And then we can break this tree down more to 5 times 5. Now here's the difference. With square roots, because it was a square root, the number 2, we were looking for pairs. When we saw a pair, we pulled it out as part of the answer, but we only counted it 1 time. With cube roots, you're not looking for pairs. You're looking for triplets. You have to find a triplet. When you find a triplet, you pull it out only 1 time. So the answer is 5. And that's the answer. And the answer is 5. Why? Because you already know that 5 times 5 times 5 is 125. We already did that. 5 times 5 is 25, times 5 is 125. So that's the cube root. But using the factor tree method is much more powerful, because if I give you a crazy cube root, like cube root of 208, then all you do is blow your factor tree up as usual. But instead of looking for pairs of numbers, you look for triplets of numbers. And I'm going to give you a preview. When you're doing a 4th root of a number, you do exactly the same thing. You write the factor tree, but instead of looking for pairs or triplets, you look for sets of 4 numbers, because it's a 4th root. If you calculate the 5th root of something, you do your factor tree as usual, but you look for groups of 5, because it's a 5th root and you pull them out. So the pattern is the same. Square roots, you look for pairs of 2 in the factor tree. Cube roots, you look for triplets. 4th roots, you look for sets of 4. 5th roots, you look for sets of 5, and so on and so on. That's all there is to it. So here we're dealing with cube roots, so we look for that. And now that we have that understood, now we can crank through some problems. 64. Cube root of 64. What do? We just go ahead and write this as what? 8 times 8 is 64. But see, this is not a square root. If it was a square root, I would just circle this. But I need a triplet, so I have to break this down, right? 2 times 4 is 8, and I'll break the 4 into 2 times 2. This 8 will be again 2 times 4, and this 4 will again be 2 times 2. And again, I'm looking for triplets, not doubles. I'm looking for triplets because it's a cube root. So this is a triplet. And don't forget everything in the bottom of your tree. This 2 is also in the bottom of your tree. That is another triplet. This guy gets pulled out, but it only counts one time because you're counting, it's a cube root. So every 3 of these you count at once. Same thing here. So 2 times 2, the answer is 4. How do you know it's the answer? If you take 4 times 4 times 4, you're going to get 64 when you do that in a calculator. 4 times 4 is 16, times 4 is 64. So this is the answer, which is 4. All right, I hope you can see that this whole process is very simple once you get the idea of it. Cube root of 8. We do a factor tree. 2 times 4 is 8. But 4 can be written as 2 times 2. And then I go and look for triplets, and I see a nice big fat juicy triplet right there. I only count it one time, so the answer is 2. Why? Because 2 times 2 times 2 is 8. That's the answer to that question. All right, cranking along here. Now what happens if we have something over here? Remember we said we can take the cube root of negative numbers. That is not a problem with cube roots. Let's take a look at negative 8. Your reflex might be to say that this doesn't exist because it has a radical and a negative sign, but that's only true for square roots, and now we also know for any root with an even number. You can't take the negative of the square root or the fourth root or whatever of a negative number. But cube roots are totally fine. Let's see how we do it with a factor tree. What times what can give me 8? I can say, let's say, well, probably the easiest way to do it is to say negative 2 times negative 2 times negative 2. That can give me 8. Why? Because negative 2 times negative 2 is 4, and then 4, positive 4, times the negative 2 again can give me the negative 8. All right? Another way to do it, if you don't think of that yourself, is here's another thing you can do. You can say, all right, negative 2, let's do an easier tree. 4 times negative 2 gives me negative 8. So you might say, well, I'm stuck because I'm going to write this as 2 times 2. I could certainly do this, 2 times 2. And you're looking for triplets, and you say, well, this is negative, positive, positive. I don't have a triplet. But then you realize that 4 can be written as 2 times 2. But 4 can also be written as negative 2 times negative 2. That's totally equivalent way of writing this, right? You don't really care about it for square roots because in square roots, you can never take the square root of a negative number. So you never try to write your factor tree with any negative numbers. But with cube roots, you can take cube roots of negative numbers because of what we've talked about. So when you write your factor tree, if it's 4 times a negative, go ahead and try to write this as product of negative numbers. And now you see that you have a nice triplet, right? Which means the answer to this is negative 2. That's the answer. Why? Because negative 2 times negative 2 times negative 2 is equal to positive 8. This gives you positive 4, but times the negative 2 gives you, negative 8 here. Gives you times that gives you negative 8, which is what I have on the inside. So the answer is negative 2. Bottom line is I'm trying to drill it in a lot. You can and you will be taking square roots of negative numbers. I mean cubed roots of negative numbers. All right, let's take a look at the fourth root. This is different. The fourth root of 81. How do we handle that? So what we do is we build a factor tree, just like always. 81 can be written as 9 times 9. But 9 can be written as 3 times 3. This 9 can also be written as 3 times 3. I'm not looking for pairs. I'm not looking for triplets of numbers. I'm looking for sets of 4, and I found one. So because of that, the answer is 3. That's the final answer. Why is it the answer? Because 3 times 3 times 3 times 3, we do it 4 times, that equals 81. And you can prove that to yourself. And that's why it works. All right, let's take another one. Let's look at the fourth root of the number 16. So we have the fourth root of 16. Again, 16 is 4 times 4. But we can't stop here. This is not a square root problem. We don't care about pairs. So we say the 4 is 2 times 2. This 4 is 2 times 2. I'm looking for sets of 4. So I see a set of 4. The answer to this is 2. That's the final answer. Why? Because the answer here, when I multiply it by itself 4 times, gives me 16. 2 times 2. Times 2 times 2. Go ahead and do that out. You'll see that the answer is 16. All right. Now let's take a look at one more thing. We said over here that we can take cube roots of negative numbers. Let's see what happens when we take negative 16 and try to take the fourth root of negative 16. What happens? There is no way to write a factor tree so that something times itself times itself times itself will give you a negative number. And you can see why from this previous problem. Because basically, the only way it's going to work to have 4 answers is going to be all 2's, just like this one. But if we choose all positive 2's, then the answer is going to give me positive 16, which is not what I have. If I choose all negative 2's, then what will happen is these will multiply to give me positive, and then I'll flip the sign again to negative, and then I'll flip the sign again to positive. So in other words, if I guess that the answer might be negative 2 times negative 2 times negative 2 times negative 2, what's going to happen is this will give me positive 4. But when I multiply this, it'll give me negative 8. And then the answer to this is positive 16. So there's no way that I can take the fourth root of negative 16, because even if I choose positive 2 as the answer or negative 2 as the answer, I get the same problem I get with the square roots. I can never get negative 16. So you say that this guy is no real answer, right? So what I was trying to say before is what I'm going to say again and again. Square roots of negative numbers don't exist. Fourth roots of negative numbers don't exist. The pattern continues. Sixth roots, eighth roots, 10th roots of negative numbers don't exist. But cube roots of negative numbers do exist. Fifth roots, seventh roots, nine roots, all of the odd number ones also exist. So because of that, we're going to write this down in a little more formal formalization. But because what you're going to find is in your book, you're going to be given a lot of really confusing looking things, but I'm trying to show them with numbers so that you understand what it's really saying. In your book, you're going to be told something like this. It'll be something like properties of radicals. So I could write this as properties. There's a lot of properties, okay? This is just some of the properties. But you might be told that you can have a radical symbol with a number n out here and a number b in the inside. And then you're told that this thing right here, this symbol here, this weird check mark here, this is called a radical, which you all know by now because I've been using it a lot. This, whatever this is, square root, cube root, whatever n is called the index of this radical. And then the number b, whatever's on the underneath the darn thing, is called the radicand. Just definitions. Whatever's underneath is called a radicand. Whatever wraps around it's called a radical. And then the index is just whatever it is. Now for square roots, we just don't even write the 2, but n would be 2. Cube roots would be 3, and fourth roots would be 4, and so on. So now that we have all of that out of the way, the property that I'm really trying to say, that I've said it many, many times, is if I have the square root, I'll go ahead and put the 2 there here just to make it clear. If I have the square root of any negative number, anything, negative 2, negative 6, whatever, or the fourth root of any negative number, right? And so on, where I might have the nth root of a negative number, where n is even, any even number, fourth root, sixth root, and so on, what you have is not a real answer. In other words, you're going to have to deal with imaginary numbers. I keep saying complex because later on, after we introduce imaginary numbers, we'll talk about complex numbers, which are related. But for now, just think of imaginary numbers. You can't take square roots, fourth roots, sixth roots, ... Anytime n is even, it doesn't work. You don't get a real answer. And I've tried to show you with examples why you never will. On the other hand, if I have the cube root of a negative number, or maybe the fifth root of a negative number, or ... the nth root of a negative number, where n can be odd, then what you have on your hands there, it is a real number. In other words, it does exist. So I'm just writing down what I've told you in words because it's actually so important that you need to understand that. For square roots, that's a majority of problems you're going to deal with. You can't take square root of a negative number. That's great. When you get to cube roots, a lot of students will say, whoa, it's cube root of negative 5. Doesn't exist. It's not true. And I've tried to show you that through problems here. But the fourth root of negative 5 doesn't exist, just like the square root of negative 5 doesn't exist. And when I say doesn't exist, I mean it doesn't give you a real answer. Imaginary numbers we'll introduce later will have something to say about that, because we will use imaginary numbers and they are very useful. All right, the next thing I want to do is I want to introduce another property. If you've paid attention up till this point, if you've watched the lessons up till this point, you realize that I've told you that you can have the square and the square root kind of cancel each other. They're kind of like opposites and they cancel each other, so they annihilate, so to speak. So if you take the square root of something that is squared, then they kind of disappear and then you're left with what's on the inside. But I've told you that you have to be a little bit cautious about it sometimes because you have this absolute value business. So what I want to do now is write down this property of radicals a little more formally, but everything that I'm about to write down is already what I've told you if you've watched the lessons up to this point. There's nothing new, but just like I wrote this other thing down we just talked about with the negative numbers and the square roots, I want to write it down to have it all in one place because it is kind of confusing at first. Okay, so let's talk about it. Let's say that in the nth root, n is odd. N is odd, because we're going to have another case when n is even. If you have the nth root of something raised to the nth power, you see, this is like the square root of b squared, where the square root and the square would cancel and you would just be left with b, right? But in this case, I'm saying n is odd. So the first case I'm going to talk about is when I have a cube root of b cubed. Later on, I'll handle the even case down below, but let's talk about the cube root of b cubed, or the fifth root of b fifth, or the seventh root of b to the seventh. You see, when you're taking the nth root of something to the nth power, you're going to get back what's underneath it, always, for any kind of an even answer. You don't have any absolute values to worry about or anything like that. Let's give a couple of quick examples. If you have the cube root of 10 cubed, the cube root and the cube on the 10 kind of cancel. You can think of it as a factor tree. 10 times 10 times 10, looking for triplets, I pull it out and I get an answer of 10. So I'm just left with what's underneath there. Generalizing it further, if I have the fifth root, because I'm looking at n as being odd, the fifth root of a variable raised to the fifth power. Same kind of thing. The fifth root cancels with the fact that I have 5 variables. You can think of a factor tree. X times x times x times x times x. There's 5 of them. I look for a 5, I have 5, I pull it out, and the answer I get is x. So basically the root cancels with the exponent, leaving you with what's underneath, exactly as it is written. It even works if you have something negative under there. For instance, if I have the cube root, again, n is odd, and over here I have negative 5 raised to the third power. I have a negative 5 raised to the third power, right? So the cube and the cube root and the cube will then cancel, leaving me with what is underneath there. So in this case, when you have an nth root and something on the inside is raised to the nth power, the root cancels with the exponent, they annihilate each other, and what you are left with is what is on the inside. In this case, we were left with 10. In this case, we're left with x. In this case, we're left with negative 5. When n is odd and you have an odd root, and something raised to an odd power underneath it, they completely cancel and you're just left with what you have. Complete cancellation. Easy to remember. Now here, the next part is the part that actually is harder to remember. And I'm sorry, it's just the way it is sometimes. I have to present it to you. You're just going to have to remember it. What happens if n is even? What happens if n is even? Then it would look like this. N root of b to the nth. Everything's the same. It's just now n is even. So this means the square root of b squared, the fourth root of b to the fourth, the sixth root of b to the sixth. You think, on the top of your head, you think that I cancel the root with what's with the exponent and I'm left with b. But actually, it's a little more complicated than that. You're left with the absolute value of b. Or another way to say it is, you're left with b, but you have to assume that b is greater than 0. That's another way you might see it written in some books. If you cancel an nth root with an nth exponent, when n is even, second root, fourth root, sixth root, and so on, you can do the cancellation, no problem, but you have to consider b, whatever's left over, to be positive, or another way you might see it written down is the absolute value. That will force it to be positive. Let me give you a couple of examples to show you why that's the case. And I have already shown you this as we've gone along. But let's do a few more, because this is quite confusing the first time you see it. Okay? Let's take an example. What if you have 7 squared, right? 7 squared, and I'm taking the square root of that. So the square root will cancel with the square. Another way to think of it is you can say this is 7 times 7 in a factor tree. Circle it, pull it out. Okay, so the answer is 7. But the more general way to say it is when I'm canceling a square root with a square and this ends even, what I'm really doing is I'm saying it's here, but it's really the absolute value of 7, which is just 7. So you don't notice that it's an absolute value because 7 is already positive, so the answer you get is 7. So because this rule seems to hold for all of these, you're tempted to think the following. You're tempted to think, what if I have negative 7 squared? And I'm going to take the square root of that guy. Then you think that what's going to happen is I'm going to cancel the square root with the square, so what I will then be left with is negative 7. But that's not right. It's not negative 7, right? So let's put negative 7 here, and you'll see why it's not right. Because in this fact, if you kind of actually do this problem in all of its glory, then what you really will have, negative 7 times itself is positive 49. Positive 49. You take the square root of positive 49, you get positive 7. So there's no way the answer to this is negative 7. Even though you think the square root's going to cancel with the square, it's going to leave you with this. It's not. Because you're doing the squaring, which erases the sign, and then you square root it, you get a positive answer back. So the rule of thumb is when you're canceling a square root with a square, or anytime it's even, you do go ahead and annihilate them and b comes out, but you have to take the absolute value of b. So really this negative 7 is what is left over, but really it's the absolute value, so you get 7. That's really the way to think about it. So the way to think about it is when you're canceling a square root with a square, because n is even, square root with a square, go ahead and cancel it, but take the absolute value of what's left over. That's the shortcut way. Here, in this case, it just happened to be positive. We still take the absolute value, we still get 7. Here, it happened to be negative. We take the absolute value, and we get the 7. Let's do a couple more real quick. Or a couple real quick examples to show you. If you had, for instance, negative 3 squared, and we're going to go ahead and take the square root of that, then what you're going to have is you think the square root's going to cancel with the square, and you're going to be left with negative 3. But really what you have, you take the absolute value of negative 3, so you always get a positive answer back. You know that that's right because negative 3 times negative 3 is 9, positive 9. Square root of positive 9 is positive 3. And then, of course, if you have just a regular 3 squared in there, then what you're doing is the same thing. You're canceling them. You have a 3, but you just take the absolute value of that. It doesn't matter, though, and so you get 3. So the bottom line is you are never going to take the square root of something and get a negative answer back. You can't. It doesn't exist, right? You can't take the square root of something and get a negative answer. So in your mind, later on down the road, when you're solving equations, when you're taking square roots and so on, there's going to be a lot of times when you're going to be canceling something that has the same value inside of here squared and the square root, they're going to annihilate. Remember to take the absolute value if it's even. This also is the same thing if this is a 4th root with 3 to the 4th or a 4th root of negative 3 to the 4th. They're going to cancel, but you'll have to take the square root of the inside to recover back the right answer. You're basically choosing the principal root there because of that. Okay, now here what we have had, let me kind of draw a little divider line here for the final thing in the lesson. Here we have had the situation where we have something raised to a power, and then we have an nth root. And we know that the nth root will cancel with that inside power. Same exact thing was here, it's just n is even and n is odd. So now we want to go the other direction. We know that squares and square roots cancel each other. Here we had something raised to a power, and then on the outside we had the nth root. Now let's write it in reverse and see what we get. If you have b to the nth root, and then you wrap that whole thing in parentheses and raise it to the power of n, you have a similar situation, right? You have an nth root of something, but then you're raising it to the nth power. These cancel just as these cancel, right? So it's kind of like, it doesn't matter the order in which you do it. If you think about it like in terms of multiplication, 3 times 2 is 6. 2 times 3 is also 6. It doesn't really matter the direction you do the multiplication, right? Because multiplication doesn't matter. This is one of the properties of math. And since these roots and these exponents all involve multiplication, the order of them doesn't really matter either. So here, when I had a power and then an nth root, they canceled. And then I got basically what was back in the inside. Here, I have the nth root and then the power on the outside, but they're still going to cancel. The n is going to cancel with the nth root, and you're going to end up with b. But when you have on the inside the nth root and then the outside power of n. It doesn't matter if n is even or n is odd. So I'm going to say any value of n. Doesn't matter if n is even or n is odd. So just to give you a couple of examples, let's say that I have 7, and I'm going to take the square root of that, so n is 2, and then I'm going to go ahead and square that whole thing. So I have the square root of 7 squared. The square will cancel with the square root, and I'll be left with whatever's on the inside, which is 7. I don't have to do square roots, I don't have to do absolute values, I don't have to think about it. When I have a root raised to a power, I just get what's on the inside. Likewise, if I have -5, like this, I'm going to take the cube root of it, and then I'm going to cube the whole thing. Of course, I can take the cube root of negative numbers. That's okay. So that's legal to write down. I'm going to have the cube root of something, and I'm going to raise that to the power. So the power of 3 is going to kind of cancel with the cube root. I'm going to be left with what's on the inside. Doesn't matter which is this guy. Doesn't matter if n is even or n is odd. The only reason this even and odd business even mattered is because when you do the squaring or the exponent first, if you have a negative number in there, it's going to change the sign of it. And then when you take the square root, you're only going to get positive values back. So you have to be a little careful when you do the squaring first and then the square roots. They still cancel, but you have to apply an absolute value in some cases. But when you do the root first and then the square, it doesn't matter at all because it's a different case. And that's just about the best I can say about it. It's just a rule of radicals and cancellation of things that I want to bring up. So it's very common to use a square root or a cube root or a fourth root to cancel, so to speak, a square or a cube or a fourth power variable. Very common to do that, but there are some gotchas that I tried to show you here, and we're going to get practice with those as we go into the next section. So follow me on to the next lesson. We're going to continue working with this. We will specifically be doing problems a little bit more aligned to these where we're trying to kind of cancel things so that we can apply this. So what I'm going to do is leave this on the board so that you can see how to apply these rules when you're kind of canceling a root with an exponent.